Barcelona, and thanks for coming to the seminar talk. So in the next 40 minutes, right, for the talk, I guess, roughly. So I'll be presenting some of the work I've been doing in the past 3 or 4 years on gravitational wave analysis with machine learning, and in particular with simulation-based inference. So I've divided the talk to give a bit of background about the machine learning side in general. So I first be introducing a bit like inverse problems in science in general, and then I will talk more about the gravitational wave side of things, and yeah, to give you an overview of what we've done. So okay, I think I need to click once probably. Yes. All right. So starting with the first section and motivating that with the gravitational waves. So we in gravitational wave inference, we have the following setup. So the gravitational waves we measure on Earth here, we know that they typically come from mergers of compact objects. So most prominently mergers of 2 black holes. So literally 2 black holes millions of light years away from Earth that spiral around each other and merge into a single more massive black hole, emitting energy in form of gravitational waves that then propagate through space and can be measured here on Earth in the LIGO interferometers, for example, and also in Virgo. Now, these gravitational waves, we know from general relativity that they come from these black hole mergers, or that we know that these systems should emit gravitational waves. And we also know that the shape of the gravitational wave depends on the system in question, right? So if the system were to look different, the gravitational wave would also have a different shape. So that means that we can, in principle, decode the information from the gravitational wave and thereby characterize the black hole system. And this is an inverse problem because the easy direction, or the direction that's typically being modeled, is the other direction, right? We can take some general relativity model or some phenomenological model that computes a gravitational wave for a given black hole merger. So if we were to know all the black hole parameters, then we could compute the gravitational wave, and we have some simulated data as shown here in red, for example. But in reality, we want to do the inverse direction, right? So we want to find parameters, in this case, the masses of the black holes, such that the simulation matches the data. And such a setup is in fact a really generic scientific setup that doesn't just occur in gravitational wave, but that actually happens or is encountered through a variety of scientific domains. So we typically have some kind of scientific system that can be described by a set of parameters. In the gravitational wave case, or in the black hole case, those would be 15 parameters describing masses and spins of the black holes. But it could also be a system in neuroscience where the parameters would be some firing rates of neurons or some network connectivity, or in material science, it could be some surface parameter of a given material. And then given access to those parameters, we typically have a forward model for our measurements. So we have some physical model that prescribes how a given physical system should manifest itself in observed data. And in the case of gravitational waves, the observed data is a time measurement, so a time series, which in our case is maybe like 50,000 dimensional time series. And this is our measurement. And this measurement could also be anything else, really. This could be, I don't know, MRI data of a brain, or it could be, in the case of material science, it could maybe be a scattering image. And inverse problems then are concerned with the backwards direction, so going from data back to the physical system and characterize the system. And a very successful way of characterizing the system is called Bayesian inference, where we basically aim to infer a posterior density, P of theta given D, over the system parameters theta, conditional on the data D. And so this is just given by Bayes' theorem, and the posterior is defined by 2 quantities. So the first one is the forward model that I've just explained, that tells you that gives you the likelihood of obtaining some data D if the underlying system parameters were parameters theta. And then we have some prior belief about the parameters. And this, if you don't have a particular prior belief, this is typically taken to be uniform. And so the Bayesian posterior, this is really a probabilistic way of solving this inverse problem, right? So this is not just a point estimate, but instead it's a probability density that quantifies uncertainties. So it has a finite width for the parameters and also correlations between parameters. So this is really kind of the gold standard way of solving this inverse problem, and it obviously also allows for stochastic forward models, right? So if multiple parameters can lead to the same observations, and the Bayesian posterior can quantify this. Now there is obviously this is like a very broad setup, and a lot of people have put thoughts into how into methods that solve this Bayesian inference problem. So previously or traditionally, one has used stochastic samplers such as nested sampling. I guess that's a more recent one, or Markov chain Monte Carlo to sample from the Bayesian posterior. Because such probability densities, obviously in high dimensional space, they are very difficult to deal with. So what you actually want to infer in the end is you want to infer samples from the posterior. So basically just sets of parameters that are representative for this density, because sets of parameters are much easier to deal with in order to compute Monte Carlo estimates, in order to marginalize out other parameters. And there's a variety of stochastic samplers, but what they all have in common is that they are based on sequential likelihood evaluations. So basically for MCMC, for example, you start in one point in the parameter space, which in this case is two-dimensional, and then you jump to another point, and depending on the likelihood there, you either reject or accept this sample, and then this way you move through the space and you build up a Markov chain of samples that in the end is representative of the Bayesian posterior. Now, a more modern method is called simulation-based inference, and this also addresses this Bayesian inference problem, but from a different perspective. So the conventional samplers, they rely on likelihood evaluations. So we move through the space and evaluate the likelihood. So we get a number. So we give a set of parameters and some data, and we get a number back. And in simulation-based inference, we also use the likelihood, but we don't evaluate it, but instead we sample from it. So in the gravitational wave case, for example, that would mean we don't ask our model, given this gravitational wave and those parameters, what is the likelihood that this is compatible, but instead we say, those are the black hole parameters, simulate me a gravitational wave. And so there's not just deep learning SBI methods, but most of them are. And the deep learning methods, they typically use a set of simulations from your forward model, and then train some kind of density estimator typically, and then inference can be performed using this density estimator. And the method that I'll be focusing on in this talk is called neuroposterior estimation, where we parameterize the posterior with a density estimator Q, which is shown here in orange, or an example of which. And then we train a neurodensity estimator to actually match the posterior for all possible measurements. And then in the end, we can use this neural network as a surrogate for the actual Bayesian posterior. And there's a trade-off between using conventional methods and simulation-based inference, and I'll talk a bit about that later in the gravitational wave section. But basically, the fundamental difference is that stochastic samplers need a tractable likelihood, and simulation-based inference only needs the ability to simulate from the likelihood, which in a lot of cases can be much allows for much broader problem statements. So, for example, what people here are doing when you simulate populations of neutron stars, and then you simulate these PP dot diagrams, right? There you can easily simulate, or not easily, it's expensive, but you can simulate. But the likelihood is really it's not tractable, right? So in that sense, simulation-based inference is a bit more flexible. However, it comes at a cost of having slower training times. So you typically need to train your neural networks. So you have to have some upfront costs that you don't have for MCMC, but then you have really fast inference. And this is the key point for us. So this is the motivation why we're using simulation-based inference. So I want to talk a bit now about how this neuroposterior estimation method works. And this is basically, it requires two steps. The first one is we need a network that can actually parameterize Bayesian posterior, and then we need a method to actually train this neural network. And I now want to introduce both of these steps. So for the density estimator, so the network to estimate the Bayesian posterior, we use a technique called normalizing flow. So this is a network architecture that enables density estimation. And the idea of normalizing flow is basically to parameterize some n-dimensional density, so in our case n is 15, by starting from a Gaussian, so with zero mean and unit variance of the same dimension, so in our case it would just be a 15-dimensional Gaussian, and then applying a series of transformation mapping this simple distribution into a more complicated distribution, such as the one-dimensional Q here. And then in order to sample from your model, you simply sample from the Gaussian here, and then you apply the transformation F to that sample, and then you have a sample from the normalizing flow. In order to evaluate the density, on the other hand, you have to go the other way. So you basically have to map your sample theta back into the space of the Gaussian and evaluate the Gaussian density at that space. And then you have an additional Jacobian that you pick up. So in this way, normalizing flows can define densities that we can both easily sample from and that we can also evaluate. And in practice, we don't just do the whole transformation in just one step, but instead normalizing flows use a series of transformations in order to go from the simple density here to the complicated density here. And one of the key results in the normalizing flow literature is that that normalizing flows can in fact be made arbitrarily expressive. So the more layers we add and more parameters we add to the normalizing flow, or like trainable network parameters, the more expressive it becomes, and asymptotically we can estimate any density with these. Okay, so therefore these networks are suitable for us to parameterize a posterior, but now we need a method such that Q actually matches P. And for that, we simply minimize the KL divergence between the true posterior P and our model Q. And so the textbook definition of the KL divergence is just the blue one here. So it's P log P over Q, but that is the KL divergence for a fixed data. And we actually want to minimize the KL divergence for all possible data. So we're simply averaging over the data. Then we do some Bayesian gymnastics. We rewrite the posterior with Bayes' theorem. We rewrite log P over Q as minus log Q plus log P. We notice that the final term, so what's proportional to log P here, that this actually doesn't contain any Q. So when optimizing Q, we don't have control over this term. So we can simply discard this because it will vanish in the gradients. And then we rearrange the integration. And what we're left with in the end is that up to this irrelevant constant, the KL divergence between P and Q is simply given as the expectation value over log Q, where the expectation value is taken with respect to parameters sampled from the prior and data sampled from the likelihood. So in summary, we can approximate the KL divergence between between the true posterior and our normalizing flow simply by creating a data set of parameters and simulations where the parameters are sampled from the prior and the simulations are then simulated with our likelihood from the corresponding for the corresponding parameters. And then we simply minimize the negative log likelihood across that data set. And then we know that this corresponds to empirically minimizing the KL divergence. Now, since our estimate Q, or our parameterization Q rather, is an arbitrary density estimator, as I mentioned before, and we now minimize the KL divergence, we know that asymptotically we should perfectly recover the posterior, right? Because the global minimum of the KL divergence is obviously achieved when we have a perfect match between posterior and our model. And another thing to note is that this technique, so this neural posterior estimation technique, actually uses the same ingredient as stochastic samplers, such as Markov chain Monte Carlo. So the prior and the likelihood, which are the ones that define the posterior, but we use different representations. So we don't use evaluation of prior and evaluation of likelihood. Instead, we use simulations from both of them. But it's really, I mean, those are just, this is just from a practical point of view that it's different to simulate and to evaluate the distribution. Of course, from a conceptual point of view, it's the exact same thing. And therefore, it also makes sense that Markov chain Monte Carlo and simulation-based inference converges to the same result asymptotically. Okay, now I want to talk about the gravitation waves and how we apply these techniques to gravitation wave analysis. So first of all, let me motivate why we want to do this, because very often, and I can completely understand this when using machine learning for science, the motivation is that you just want to use machine learning. And that was also my motivation when I originally got into machine learning, back before I started with this application. But actually, and don't get me wrong, like obviously in the end, there's like very good applications for machine learning across a lot of different fields of science. But I feel it's always important when you start out such a project that you exactly know what problem you actually want to solve, because otherwise you'll the community won't appreciate you doing things that have been done previously, but now you do them with machine learning and write a fancy paper about this. But in gravitational wave inference, we actually have a lot of problems, and one of them is that the computation that methods such as Markov chain Monte Carlo, they are really expensive. So for semi-expensive gravitational wave models, they can sometimes take days or even weeks for the analysis of a single event. And back in 2015, we had like 2-3 events, I think. But now, like the event rate is heavily increasing, and with next generation detectors, we'll get many events per day. And then obviously such high inference times can become problematic. And the second limitation related to the speed is that for some events, such as neutron star mergers, you actually want really fast inference because you want to know where the gravitational wave is coming from, so you can align electromagnetic telescopes for potential follow-up search. And secondly, stochastic samplers can be inaccurate, not in the sense that the inference method actually is inaccurate, but in that they impose assumptions that can make the whole analysis inaccurate. And the first one is that very expensive gravitational wave models are also really expensive with stochastic samplers. So we have to use the cheaper gravitational wave models, which may these days, I'm not an expert on this, as good as the more expensive ones, I'm not sure. But fact remains that MCMC struggles to scale to such waveform models, leading to systematic errors, right? If you're using the wrong model or like an inaccurate model, you have inaccurate inference results. And the second thing is that stochastic samplers actually require tractable likelihoods, as I mentioned before, which in gravitational wave means that you have to make simplifying assumptions on your detector noise model. Whereas for SBI, in principle, you could just simulate gravitational waves with real detector noise, and you would have a noise model-free inference. So those are the motivations for using SBI, and basically, so we have addressed like those three of them. The noise model-free inference, that is something that we still hope to do one day. Okay, so I mentioned that we need a simulator, or in other words, a likelihood simulation. And in gravitational waves, this is set up in the following way. So we assume that the measurement consists of signal and noise, and the signal can simply be computed from a general relativity model. So like lots of people are developing very good models for these, and those are deterministic computations that compute the gravitational wave based on the black hole parameters theta. And by the way, I'm not sure if I've mentioned this, we have 15 parameters theta. So we have 2 masses and 6 spins for the black holes, and then 7 parameters for location in space-time and Euler angles. So the gravitational wave can be computed from these 15 parameters with some general relativity model. And then we assume that on top of that, we have stationary Gaussian detector noise. And the amplitude of that noise is determined by the so-called power spectral density, which is just a property of the detector noise, and that can just be empirically estimated using signal-free data around the time of the event. And this way of setting up the likelihood, of course, corresponds to a tractable likelihood, where in order to compute the likelihood, you subtract the gravitational wave for parameters theta from your data, and then compute the probability that the residual is indeed a realization of Gaussian noise. And then our inference net, right, this is the simulator, and then the only other thing we need to define is a prior, and for that we use mostly uniform priors, and this then defines our Bayesian posterior fully, so we can then do simulation-based inference with the way I've described before. And so this is how our inference network looks like. So we have the normalizing flow here at the bottom, which transforms the Gaussian into the Bayesian posterior for the black hole parameters theta. And that is, of course, a conditional distribution. So for different gravitational wave data D, we'll get different posteriors, of course. And the conditioning is achieved via taking the gravitational wave data, which is roughly 70,000 dimensional, depending on the setup. We feed that through an embedding network with, I'm not sure, like something like 60 layers or so, and then transform this gravitational wave data into a compressed representation that in this case has a 128 dimension, it's just a 128 dimensional feature vector that then conditions the normalizing flow. We also condition our posterior on the detector noise PSD. And what this allows us to do is it allows us to instantly tune our inference result to changing detector noise levels, right? So during an observing run, the noise level within a detector is in fact not constant, but it can vary depending on detector improvements during the run, or actually can also get worse. And we simply condition the posterior, so we just simply consider that also as data. And then we train the whole thing end to end. This particular setup can be trained in 3 days on an A100 with batch size 4,000, and we use roughly 2 billion simulations. Only 5 million of them are unique though, across the expensive axis. And then once this is trained, we can perform inference in roughly 20 seconds per event. There's also a component that I'm not going to talk a lot about, which is like an iterative algorithm that we came up with to simplify the data, which is crucial for the performance. And I have a couple of slides on this, but I think I'm not going to go into much detail on this. So the full setup is called Deep Inference for Gravitational Wave Observations, or DINGO. And so for those of you who are familiar with the gravitational wave community, there's another inference library which is called BILBY, and this stands for Bayesian Inference Library, which is an Australian, a little Australian memo. And this is basically the gold standard for gravitational waves. And as the new kids on the block, we decided to name our tool after a predator of the BILBY, the DINGO. So at least that's what people think. For us, it's obviously just an acronym. Okay, so now turning to evaluation on real events. So this is 150914. So this is the Nobel Prize winning gravitational wave, which was incidentally also a very clean gravitational wave event. So very good data set to benchmark on. And so we're comparing here DINGO against an MCMC run that took about, I think, 2 or 3 days to complete. And we find that basically across all parameters, so we're obviously just looking at the marginals, but the marginals are basically identical between DINGO and MCMC. Same here for the sky position. Also showing another event here. This is 170817, 14 actually. This is the first 3 detector event that has ever been measured. And this is also why the sky position is so well constrained, because it can be constrained simply from triangulation of the gravitational wave signals. And again, we find really good agreement with MCMC. So in the first paper, we analyzed on 8 gravitational wave events, and we compared in terms of the Jensen-Shannon divergence. So we compared the marginals for all parameters for all gravitational wave events we analyzed. And we found really, really small deviations across all of these 8 events. We found a mean JS divergence of less than 1 millinut. Generally in the gravitational wave community, I think this 2 millinut bound has been established as kind of the indistinguishability bound for posterior. So at that point, it's really like not a meaningful difference. And also notably, we ran MCMC 2 times with different random seeds but identical settings, and this had a deviation of 0.7 millinut from each other. So that's really like fundamental lower bound. We can't get better than this, of course, or at least not closer to MCMC. MCMC may, of course, be wrong. By the way, also when I'm saying MCMC in this talk, sometimes it's also nested sampling, but I don't always want to say stochastic sampler. So MCMC is really a proxy for all stochastic methods that are out there. Okay, so now I want to turn to a problem that we had back in the day when we had these results and were really excited. But then we realized, okay, so whenever we analyze a new event and we kind of want to make gravitational wave inference cheaper, at least for like mainstream events, and we don't want that in the future when we have event rates of many per day that we have to run expensive standard samplers for all of them. But then we realized people only really believe us when we compare to standard methods, right? And it's probably also correct to do that, because machine learning in the end is a black box. I mean, we kind of have an understanding of what's going on, but we do want some independent comparison for our results, right? So back then we were puzzled how we can actually verify that our results are correct without running the very expensive samplers that we kind of maybe not want to replace. That's a bit too big of a statement, but at least that we want to provide an alternative to. So what we came up with in the end is maybe a somewhat straightforward idea, but we realized that if we get good enough at inference, we can simply apply importance sampling. So importance sampling is, of course, like a likelihood-based method, but in our case, we have both. So we have the ability to simulate the likelihood, hence we can do SPI, but we also have the ability to evaluate the likelihood, which is what MCMC relies on, of course. So what we can do is we can say the DINGO result or the NPE result is actually not the final result. So the NPE result here is sketched in orange, but instead we say this is just a proposal distribution that we use to then importance sample the target distribution. And so importance sampling works as follows. We sample from our proposal distribution, here the orange one, and then for that particular point in parameter space, we evaluate the proposal density, so the orange one, and we also evaluate the target density, which is the blue one. And then we simply assign an importance weight to this sample that, that is given by the ratio of these two samples. And what this will do is in spaces where we oversample, it will downweight the samples. And in spaces of the parameter space where we undersample, it will upweight the samples, right? And importance sampling is, I mean, this is a well-known method, very old, I guess, and it's a way to get exact samples from the posterior, right? However, this only works if the proposal distribution actually covers the entire target distribution. So if it were not to cover it, so for example, if we were to miss a mode completely, we can't sample this. So in principle, we would assign infinite importance weights, but we never sample this, right? So then importance sampling fails. But luckily, as I mentioned before, NPE is trained with the KL divergence between P and Q, but the KL divergence is asymmetric. And the direction that we train with actually is called the mask covering direction. So this is the direction where you may have seen this image if you want to fit a bimodal Gaussian with only a one-dimensional model distribution. Then you can either like fit one of the modes, so you go into one of the modes, or you kind of fit the center of the Gaussians. And the direction of the KL divergence that we're using is the one that fits the center and that kind of covers both of them. So this means that we always expect NPE to be mask covering, to be covering the entire posterior. And in fact, if it were not on in-distribution data, we would have a diverging validation loss, right? Because we would then evaluate the log the density at some point in parameter space where the model thinks there's none, right? So then we would have a diverging training loss. And in fact, we sometimes do see this, and then we need to start the model in a different configuration. But given that we have a finite validation loss, we always know that our estimates are mask covering. We've also verified this empirically for gravitational wave data. And this means that we can actually, in fact, use importance sampling. So importance sampling really was a game changer for us because it has mostly independent performance metrics that we can assess without actually comparing to an alternative method. And the most important one here is the effective sample size. So the effective sample size is simply computed by looking at the variance of the weights. So if all weights are the same, if all weights are 1, then we have an effective sample size that is just equal to n. And if the weights have a bigger variance, then the effective sample size will be reduced. And the sample efficiency is simply then the number of effective samples divided by the number of actual samples. And intuitively, the effective sample size tells us that our weighted samples, so maybe we have 100,000 samples, and the effective sample size is 5,000. This then tells us if we use the 100,000 samples with weights, this is as good as using 5,000 unweighted samples from the ground truth posterior. So it's very easy to interpret this number. And the second thing that we have that basically comes from the normalization of the weights is actually a very precise estimate of the so-called Bayesian evidence, which is the normalization of the posterior. And this is useful, for example, for a model comparison. And it turns out that the statistical uncertainty of this actually scales with 1 over square root of n. So by simply sampling more at inference time, we can get really precise estimates of the Bayesian evidence. And just to show how this works in practice, so when we used a more complicated gravitational wave model in a second follow-up project, we actually found that the posteriors were not quite matching MCMC all the time anymore because the problem has become more difficult and we used the same neural networks. But after importance sampling, we basically found again perfect agreement almost between the reference posteriors with MCMC, for example, and our importance sample posterior. So we evaluated on a bunch of events. Now we evaluated on half of the gravitational wave events that had been detected up to that point, and we found that we in general had really good sample efficiencies. So depending on the gravitational wave models, we had sample efficiencies of 5 to 37%. So 5 was for the most expensive waveform model, and 37 for the one that we started out with in the initial results. And the Bayesian evidence that we estimated was generally consistent with nested sampling, but a lot more precise in our case. Also, one interesting thing that we found is that low sample efficiency kind of flags failure of the model because it tells you that you don't really have the mask covering posteriors anymore, and that you have some light-tailed proposal distributions. And we actually found that low sample efficiency could flag things like adversarial attacks. So when we were adversarially attacking our model, so deliberately giving it corrupted data, we actually found that, of course, the model produces something that looks like a posterior, but after importance sampling, you get only one effective sample, and then you know you can't trust it. And the same thing happened for glitches, for example. So when analyzing noise glitches in the detectors instead of gravitational waves. Yeah, so this importance sample extension to MPE is, of course, quite a generic method. So it's not limited to gravitational waves, but you can use it whenever you have a tractable likelihood in addition to the ability to simulate it. But the caveat is that it's an extremely aggressive metric. So you need really, really good posteriors such that it actually works. And the reason is that while in one dimension, so when you look at the marginals, they may overlap perfectly with what you consider the ground truth distribution. Importance sampling really works in the full n-dimensional space. So in our case, 15 dimensions. And that, of course, means that that small deviations along just one axis that you may not see in the marginals can lead to terrible sample efficiencies. But when it works, then it's really a great confirmation that your results are in fact correct. Okay, so the final thing I want to do is I want to talk about like four different projects and only give like 1 or 2 slides on these because we just lack time to talk about all of these things. But I still want to kind of share the some of these things. So the first one is an algorithm that we came up with to include symmetries of our model. And maybe the most obvious one in gravitational wave inference is the symmetry under time shift. So we work with Fourier transformed time series, so frequency domain data. And if you apply like this local phase shift to the data, then you know that this is just a time shift, or it just corresponds to time shift. And therefore the posterior across all parameters should remain the same because we have stationary noise, except for the time parameter, which we also estimate, which should be exactly shifted by the amount that you time shifted your data. So that's a symmetry of your forward model, of course, so of the physical model, and it translates to a symmetry of the posterior. But NPE learns such data just based on simulation, so it gets lots of time shifted data, and then it will realize in the end it will learn just from the data, okay, those are actually all the same posteriors, only that I have to apply the time shift. And that, of course, is somewhat of a wasteful approach if we actually know the symmetry in advance. So we try to come up with an algorithm that can enforce such symmetries by construction. And the way we integrate this in the end is a somewhat intricate algorithm, but it basically tries to this algorithm basically standardizes the data around a fiducial value for the symmetry parameter. So in this case, always t equals 0, for example. And then at inference time, we need to use an iterative inference scheme over some nuisance parameters that we need to add to the parameter space in order for this to work. And this is also the reason why inference in the first paper I talked about takes 20 seconds and not 1 second as one forward pass of the neural network would. And for gravitational waves, we found that we actually had really good accuracy improvements. So this is MCMC compared to NPE after all of the hyperparameter and engineering optimizations that we used in the final paper. And then when we just turn on the symmetry enhanced GNPE, we find that we get much better agreement with the reference distribution. So while this is really complicated and actually we lose access to the density, which we need for importance sampling, and then need to regain in a very, very expensive step. So we're kind of trying to get rid of GNPE, but it's just so important for our performance in the gravitational wave sector. And I guess maybe it's also nice to see that even that just upscaling your methods does not always perform better than trying to integrate some physics. I mean, maybe, at least at the time, I found this a nice lesson. Okay, so GNPE is an iterative algorithm, and so for the sake of this illustration, I have initialized GNPE deliberately with some bad initialization, and then we see how within 15 iterations or so, it integrates the symmetry and converges to the true posterior. And this is in real time, by the way, so I adjusted the time of that animation roughly to the time it takes on an A100 GPU to do inference. Okay, so another project I very quickly want to talk about is a project where we looked into something very similar to neuroposterior estimation, but where we actually replace the density estimator with a continuous normalizing flow. And continuous normalizing flows are really great because they require much fewer parameters. They just need to parameterize a vector field, in our case in 15-dimensional space. So we can get rid of the entire density estimator. But the issue is that continuous flows are notoriously hard to train, because at inference time, you actually need to integrate an ODE, so an ordinary differential equation, which means that at train time, if you train with maximum likelihood, as we do for NPE, you also need to perform this integration, which makes training completely infeasible typically. But there was a recent method called flow matching, which has been applied to like generative models, so images mostly. Here, this paper, I want to highlight this. I think this is a really cool paper. And this is somewhat similar to diffusion models, but has a few other properties. And we basically looked how we can apply this flow matching training objective to SBI. And we found that it scales quite a bit better than NPE, and that we also find improved accuracy, although it's a bit more expensive at inference time. Yeah, so this is just a comparison. And another project I want to highlight is a project that was led by Niha, where we actually try to use DINGO for science, which of course is the final objective that we hopefully achieve over the next few years. And so basically in this project, what Niha looked at is whether we can identify eccentricity in the black hole population. So he analyzed 57 events, so basically all of the events that have been measured so far that fall within the prior for the masses that we can currently scale to. And then he analyzed these events very thoroughly with multiple different noise subtraction methods and multiple different waveform models. And the goal of that study was to figure out whether we can find evidence for eccentricity, so basically non-circular orbits for these gravitational waves. And the reason why this is meaningful is because this tells us something about the dynamics of the formation of these black hole systems. And what he actually found is that there's like a few candidates that very much look eccentric. So this axis is the axis for an eccentricity parameter, and circular orbits would correspond to this parameter being 0. And he found a few events where we actually have very little posterior support for 0 eccentricity. And there's a few caveats to this study, like in particular how glitches were subtracted, because there's no consensus on this, and also the waveform models are not quite as accurate, or like they don't incorporate all of the physics that we need to make like a definitive statement. But what he came up with in a very thorough statistical analysis is that there's at least a 0.5 or at most a 0.5% chance that none of the events we've seen so far is eccentric. And I thought that was a really cool application, although I don't understand all of the ins and outs of the analysis he did. And I should say, like, the reason he used DINGO for this is because he ran with very expensive waveform models that actually include effects such as eccentricity. And repeating this study with like a stochastic sampler would have been completely infeasible from a computational point of view. Yeah, and the final thing I want to highlight is something that I'm actually working on just now, and by now I mean like basically any minute. I'm not giving this talk at the moment, and that is the extension of DINGO to the merger of binary neutron stars, and which is very similar in terms of the setup, but it has much longer signals, which makes it extremely challenging. And but on the other hand, this is actually where we can have the most impact, because if we can do very accurate inference for neutron stars, we can prompt the telescopes really early on, maybe even prior to the merger, to actually measure maybe precursor counterparts even. So this is those are some preliminary plots for a SkyMap I generated when analyzing signals that are actually over an hour in length, so 1,000 times longer than what we've previously done. And we see that 15 minutes before the merger, we have quite good localization already. So this is for Cosmic Explorer. This is an injection into a future next generation detector. Okay, so finally, want to thank you for your attention. I obviously haven't done all of this by myself, although it seems like it when I talk about it, but I have a bunch of great collaborators that I want to highlight, in particular Stephen Green, who's a very close collaborator on this project. So those are the papers that I've talked about, and I'm happy to take questions.
Thanks a lot for the very interesting talk. I don't know if there is any question for Max.
Not an experience. I was interested in, for the success of your method to be high, let's say. So how much depends on the training set? So because you have to simulate of these waveforms for the system. So how many simulations and how accurate they have to be, let's say.
Right. So in terms of the accuracy, I get that out of the way first. I think we are really lucky in the sense that we have that we have like only very small mismatches between the waveforms that people have done have come up with at LIGO and the actual data. So so I think there, like the accuracy of all of the waveform models is enough such that that none of the real events is really out of distribution, unless they are highly precessing also. So there's like a few events that are a bit tricky to estimate with SBI. In terms of the dataset size, that is something we've been continuously increasing over the last years. So back when I joined this project, so Steven worked on this, I think like maybe 1 year also before I started, and he started with 100,000 simulations. By the time I joined, we were using 1 million. Then we've been using 5 million now for the past 2 years or so. And like for the final project, Cosmic Explorer, we're using 60 million simulations. So so we realized at some point, okay, it's not enough anymore, and then we just generate more data because luckily in our case the simulator is it's not as expensive as for you. Yeah.
So it's not really that expensive to generate all these waveforms.
Right. So with the simulator that we're using for the neutron stars, the 60 million waveforms can be generated in a few hours on our cluster. We have run inference, like in particular, this eccentricity project has been done with a simulator that takes 3-4 seconds, I think, for a single evaluation. So they are like generating 10 million waveforms is expensive, but in contrast, and maybe almost as expensive as a single MCMC run. But in contrast to like the sequential stochastic samplers, we can do it fully in parallel. So we don't have to do it on one CPU and wait for it, but we can generate a data set of 10 million waveforms on thousands of CPUs.
And then regarding this important sampling that you do, because it seemed to me that you need to have some knowledge of the Bayesian posterior.
Yes.
It's not. So because then I don't see exactly what I mean. It looks to me a bit circular, the algorithm, but maybe it's because I don't fully understand it.
It's simple, the algorithm, you mean? Yeah, it is simple.
No, I mean circular. I mean,
circular.
Because in the end, what you want to get is the posterior. Right?
Yes.
So, and you seem to mention that you need to have some knowledge of to determine this weight.
Right.
So how does it work?
So we do, like in simulation-based inference, you don't assume that the likelihood is tractable. But in our case, we do have a tractable likelihood in addition to the samples that we generate for training. So we can evaluate the target posterior, which is this up to, which I'm dropping here, up to a constant. So the posterior is just have it on this slide, right? So the Bayesian posterior is just likelihood times prior divided by this evidence, right? So this evidence that we don't know, but we can evaluate the likelihood and we can evaluate the prior. So we can evaluate the unnormalized version of the posterior. And then what we do is we do self-normalized importance sampling. So this is self-normalized importance sampling basically is the adaptation of importance sampling to cases where this density is not actually normalized, but we can evaluate the posterior up to this constant, and that means we can actually do importance sampling, and it's not a free lunch in the sense because just like even if we could evaluate the normalized posterior, even if we could do that, sampling from it is still very different, right? It's still very, very challenging.
Since you are thinking about doing hours-long data, like do you have to deal with non-stationary noise in that
right? That is that's an excellent question. That is and that is something we completely ignore for the sake of this plot. So I mean, for neutron stars, they are typically like the two that LIGO has detected so far. They're like 128 second in length, I think, for the analysis segment. So I think for that, you don't have to think so much about non-stationary noise. But obviously, like when you do hour-long signals, then yeah, you would have to do this. The point of this study, so this is really not like a main result of that paper. That is just to show that the compression that we're using in order to compress these long signals, that this actually works for very long signals. It's not to say that in a realistic setting, this can actually deal with all of the non-stationarities. definitely think you would have to deal with non-stationary noise for this. Yeah. And the way to incorporate this would be to just train with non-stationary noise. I mean, you can come up with models for this, right?
Yeah.
I was curious in the you used MP with the symmetry.
Right,
Could you get to that?
Yeah.
You had like a simulation where you started out with a very bad form, but as the iterations went on, it fits the previous forms. But I was wondering, as the iterations go on, it fits more properly. But at which point do you know to stop? Because in this you have the MCMC data to compare to, but besides that, how would you go about saying like, oh, this is the iteration that would work?
So in the first paper, we answered this question with the scientific rigorous answer of 30. So 30 iterations. No, but I mean, like, I agree. It's very tricky to know when to stop. Basically, what you can do is you can just look when have you achieved convergence. So like if after 30 and 40 iterations the posterior hasn't changed, then you are converged, right? The problem is, how do you say that two distributions are the same in high dimensional space, not just in terms of the marginals? And that is actually something that that is a bit tricky. And for later events, so in the actual important sampling paper, we had to increase that to 100 or 200 or 500 iterations, just so it covers all of the events, because it was a bit tricky coming up with something that actually identifies this itself. And I think the reason we are not looking into like a better engineered way of self-stopping is because we need to get rid of GNP. And actually the neutron star results, I'm not using GNPE. I'm just scaling, using bigger networks to get rid of this symmetry stuff because it's not fast enough. So that's why, I mean, conceptually, you can come up with a way that just assesses like that two distributions are the same even after one iteration. And in practice, we haven't done this because ultimately we want to get rid of this again. Thanks.
Another question. Let's check Zoom for
if
there is any question there. But
if I'm allowed, I will ask a question.
yeah, please, Vanessa.
All right. For the final plots that you showed for the localization, you used Cosmic Explorer. But did you try and do this also for ET? Sorry, not for ET, for current like advanced LIGO. Can we do this like we don't have to wait like 20 years? Can we do it now already with like
so the issue is at the noise levels? I mean, actually, the way I've done the Cosmic Explorer experiment is I have used CE PSDs for LIGO. So I've injected these into the LIGO detectors. So this is actually like with the LIGO coordinates with Hanford and Livingston. The reason we can't do this even at design sensitivity is because the noise levels are simply too high. I mean, we could do this if the binary neutron star was at 1 megaparsec, then we could do this. But at realistic distances, I think advanced LIGO doesn't work. I mean, what could work is this A-star detector. I'm not sure what it's called, where they want to use ET technology in the LIGO tubes, right? Okay. That could work. Okay. I'm not sure. Yeah.
And do you need multiple detectors in principle?
Yes, this is also. I mean, ideally you have 3, then you get really good localization. And in the CE experiment, actually, the localization that I've shown is quite good, but considering the SNR, so the signal to noise ratio of these events, it's actually not good because we only have 2 detectors. So at a much lower SNR, but with 3 detectors, the localization would be even better. I think what they are planning, though, I'm not sure, is to use like 2 detectors, like 2 next generation detectors, and then maybe use like the current ones as like an auxiliary channel that I have.